So the previous few lessons we looked a lot at equilibrium situations. We're going to start to do in this lesson is start to look at situations where an object is not in equilibrium, meaning that the net force acting on the object is not zero, and trying to figure out how do we begin to solve these types of problems. I'll point out that the technique to solve these types of problems is very similar to the technique that I use for equilibrium problems, with one key difference. And the key difference is that in at least one direction, I'm going to say the sum of forces is equal to mass times acceleration. The reason for this is if all the forces do not add up to be zero, we now have a net external force acting on the object. And by Newton's second law, we know that object is going to accelerate. So let's look at a quick example problem here to again begin to think about this. And this involves the elevator in Fayfield Hall. And I've actually measured the acceleration of the elevator, and this is actually pretty close to what the acceleration of the elevator is. So I have a mass of about 65 kilograms, and I'm going to ride in the elevator from the first floor to the second floor. And so what happens is the elevator accelerates upward with a magnitude of 1.5 meters per second squared as it speeds up and slows down. So it starts at the bottom, starts at rest, it speeds up until it reaches whatever the constant velocity is the elevator travels between the two floors, and then it slows down when it gets to the top. The acceleration of the elevator, both speeding up and slowing down, happens to be the same in the Fayfield Hall elevator. I want to determine the magnitude of the normal force that the floor of the elevator applies on me during 3 different time periods. The time period that the elevator is speeding up, so in that period between when the elevator starts to move upward and when it's traveling between the floors at a constant speed. I want that middle portion, the traveling in the floors at a constant speed. And I also want to know what that normal force is as the elevator slows down at the top. So let's do part 1, the speeding up part first. So I know the acceleration is in the upward direction. I start at rest and I'm going to end up moving upward. I know that my weight acts downward, mg, and I know the normal force acts upward, and I'm just going to call it n. And so I could say sum of all my forces is equal to mass times acceleration. My net force is going to be normal force minus weight, and that's going to be equal to my mass times my acceleration. And so I could add my weight over the other side. I get that my normal force is equal to my mass times my acceleration plus the acceleration due to gravity. And if I work this out, I get that the normal force I experience is 734.5 newtons. What this means for me in the elevator is this actually changes what my experience is in the elevator, or how heavy I actually feel I am. It's worth pointing out that your perception of how heavy you are is more related to normal force than the force of gravity acting on you. You feel the surface pushing up on you a lot more than you feel gravity pulling down on you. In fact, that's how you perceive what your weight is. So in this part of the elevator's motion, starting on a floor and accelerating upward, I'm going to feel heavier than what I normally feel during that time period that is speeding up in the upward direction. Let's go to part 2, the constant speed part. And the thing to point out about constant speed is that the acceleration is 0. Oh, look, this is equilibrium. I have my weight, my normal force, sum of force equals ma, but I know that that has to be 0. So I could say normal force and weight equals 0. I can actually solve it out the exact same way that I did before. Solve it out, I could plug 0 in there, and I get 637 newtons. And so that's my weight, what I would normally feel as my weight. So as the elevator is moving at a constant speed between 2 floors, I don't feel any different than what I would normally feel. Now this is important to note because this would work both traveling in the upward direction and traveling in the downward direction in the elevator. If I did not know what button I had pushed and I didn't know what happened in part 1, but I'm stuck in part 2, I would have no idea whether I'm moving upward, moving downward, or sitting at rest. The nice thing about elevators in this example is that an elevator is in a closed box. You can't really see what's happening outside the elevator. 3 is the slowing down part. And in the slowing down part, the acceleration is actually in the downward direction. How I know it's in the downward direction? If you're moving upward and you're going from some constant speed to rest, you must have an acceleration in the opposite direction you're traveling. So I have my weight mg, my normal force. I can actually do the exact same steps that I did before. F equals ma. normal force minus weight equals MA, MA plus mg equals normal force equals m plus a plus g. Plug it all in, and I get 539.5 newtons. So this means in this slowing down part, as I'm traveling upward in the elevator and slowing down to a rest before the doors open, I actually feel during that moment of time a little bit lighter than what I would normally feel or normally experience my weight. So that's a good example of a one-dimensional problem dealing with this concept of non-equilibrium. But what if I had multiple dimensions or multiple directions acting? Here I have a crate that's on a floor. This crate is initially at rest. I said it has a mass of 50 kilograms. I'm going to apply a force of 480 newtons on the crate, which is enough force to get the crate to move. So what this says is that 480 newtons is greater than the maximum static frictional force. We do know the force of friction that acts on the crate as it moves is 450 newtons. So that's really the kinetic frictional force acting on the crate. I want to know how much time does it take to push the crate 5 meters, and I want to know how fast the crate is moving after it's traveled 5 meters. Now, if I look at these two questions, these almost look like kinematics questions from Unit 2. I'm looking for time, I'm looking for speed, I know an initial speed or initial velocity, I know a distance or a displacement. I need to know one other piece of information, and the other piece of information I need to know is acceleration. So is there information that I could find acceleration? And the answer to that question is yes. I know information about the forces acting on the crate. First of all, in the vertical direction, I have two forces, weight and normal force. Since this crate is not going to accelerate up or down, I'm going to say weight and normal force are the same thing. I have two other forces. I have this applied force, 480 newtons, and I have this force of friction, 450 newtons. So if I look at the information I know the mass is 50 kilograms. I know the initial velocity is 0. I know the displacement is 5 meters. I don't know the acceleration. I don't know the time, and I don't know the final velocity. Those last two are things I'm actually trying to figure out. So maybe I want to figure out what the acceleration is. If I knew what the acceleration was, I could figure out the time, and I could figure out the final velocity. Both of those would be possible. So find the acceleration is my first step. And I'm going to use net force equals ma as my trick to find the acceleration. Well, if I do the net force, 480 minus 450, it's 30. 30 equals 50 times acceleration. So my acceleration is 0.6 meters per second squared. So now I know that piece of information. From here, I can now use one-dimensional kinematics, the toolbox equations, to find both time and final velocity. So do kinematics. I can use this equation to figure out the time. I know initial velocity is 0, so x equals 1/2 at squared. Looks like I multiply by 2 and divide by a, so 2x over a is t squared. And it looks like I divide or square root both sides, and I get t is 4.08 seconds. So it takes a little more than 4 seconds for these forces to push this crate 5 meters. Now at this point, there are several techniques I could use to find the final velocity. I'm going to use probably the easiest one. If I know the time, I could say v equals v initial plus a times t, and plug it in and get 2.45 meters per second. Another one you could use is final velocity squared is equal to initial velocity squared plus 2 times a times x. If you happen to do that, you get 2 times a times x. That's 6. If you take the square root of 6, you get 2.45. So you could actually do it either way and get the same answer either way. In the next lesson, what we're going to look at is a very specific example of a device that uses this concept of non-equilibrium to accelerate masses called an Atwood's machine. And we'll look at what kind of makes the Atwood's machine interesting and what are some things I need to watch out for if I have this type of situation or I'm dealing with this type of problem.